All right, let's talk about Einstein. You hear his name and you probably think of things like E equals mc squared or spacetime. But what does that actually mean? Today, we're going to get a real gut-level feel for one of his biggest ideas by solving a genuine cosmic mystery, the strange little wobble in Mercury's orbit that had scientists totally stumped for centuries.
So let's dive right in. Before we can get to the incredible solution, you really have to appreciate the problem. And yeah, it all kicks off with the planet Mercury, the one scooting right next to the sun.
Okay, so in school, we all learned that planets trace these nice, neat ovals, ellipses, around the sun, right? Same path, over and over. Well, Mercury doesn't. Its orbit isn't locked in place. The whole ellipse actually rotates very slowly over time. Imagine it's like a hula hoop that's not just spinning, but also wobbling. The big question was, why on earth is it doing that?
Now, astronomers weren't completely in the dark. For a long, long time, they knew that the gravitational tugs from all the other planets, like Jupiter and Venus, were responsible for most of that wobble. They did the math, and it accounted for about 92% of it. But that last 8%, man, it just wouldn't go away. It was a stubborn, nagging little anomaly that Newtonian physics just could not explain. It was a huge mystery.
So if you ask a physicist about that missing 8% today, they'll probably say something like, oh, that's space-time curvature. And you'll nod, but what does that mean? As this quote says, it's just a buzzword. It doesn't actually help you picture what's happening. Well, we're going to fix that right now. Believe it or not, the first clue to solving Mercury's wobble has to do with light. Yeah, light. There's this brilliant little thought experiment from an author named Louis Epstein that just cracks the whole thing wide open. Okay, picture this with me. You're in space, and you shoot a laser from point A to point B. You time it. Simple enough. Now let's do it again, but this time, we're going to stick a huge planet right in the middle of the path. So, does the light get there faster, slower, or does it take the exact same amount of time? What do you think? Get this. The answer is totally bizarre. The light actually takes more time to make the trip when the planet is in the way. Now, wait a second. Shouldn't gravity give it a little boost, speed things up? And that's exactly what's so weird. If you threw an apple along that same path, gravity would absolutely grab it, accelerate it, and it would get to point B faster. But light gets there slower. And this isn't some trick where the light itself is slowing down. Its speed is constant. No, the only way this is possible is if the path itself has somehow gotten longer. And this right here is the absolute heart of it all. The path is longer because a massive object like a planet or a star literally creates more space around it. This is the big idea called spatial curvature. A massive object warps the fabric of space itself, creating extra distance between 2 points. And here's the part that really messes with your brain. The points themselves haven't actually moved further away from each other.
I know. You're probably thinking, hold on, that's impossible. How can you add distance between 2 spots without physically separating them? It just doesn't make sense in our everyday world. But don't worry, there's a really simple way to picture this.
Imagine space is just a flat sheet of paper. The distance between 2 dots is a straight line. Got it. But now, what if you pushed up from underneath and created a little hill, a little bump in the middle of the paper? You've just added more surface area, literally more paper, between those 2 dots. The dots on the edges haven't moved an inch, but any path between them now has to go up and over that bump, which is a longer journey. That bump, that is the more space. Okay, so the bump analogy is pretty good, but we can do one better. Let's actually prove this whole thing with a little hands-on model that shows you exactly how this more space idea forces a straight line to become a curve. You should seriously try this, it's so cool. Just grab a paper circle, cut a line into the center, and then overlap the edges to make a little cone. Tape it up. That cone is our model for curved space. Now here's the magic trick. Untape it, flatten it out, and use a ruler to draw a perfectly straight line right across it. Then just tape it back into a cone again. And would you look at that? The line you drew, which you know was perfectly straight when the paper was flat, is now a beautiful bent path on the surface of the cone. That's it. Light always takes the straightest path possible, but in curved space, the straightest path is a curve. You just did a general relativity experiment on your kitchen table. How cool is that? So, this idea of more space or spatial curvature is clearly a huge deal.
But how did it fit into Einstein's own journey? Well, turns out it was the final missing piece of the puzzle that turned what could have been a huge mistake into his greatest moment.
Now, you might have heard another explanation for why gravity bends light, that it's because time itself slows down near a massive object. That's a real thing called time curvature. So, which one is it? Is it the slow time, or is it the more space we just demonstrated with our paper cone?
And the answer, brilliantly, is that it's both. They are not competing theories. They are two parts of the same phenomenon. Think of them as two different ingredients in the same recipe for space-time curvature. And Einstein's general relativity was the theory that finally put both of them together. Just look at this timeline of how he figured it out. Back in 1911, Einstein had only worked out the time part, the time curvature, and his prediction for how much starlight should bend around the sun was actually the same as the old Newtonian prediction, nothing special. But by 1915, he realized his error, he added in the more space part, the spatial curvature, and his new prediction was that the bending would be exactly double his first guess. And then in 1919, an eclipse experiment proved it. The 1915 prediction was right on the money, and Einstein became world famous overnight.
Okay, so we've got all the pieces. We understand more space, we understand how it fits with slower time. Now let's bring it all back home and finally close the case on that weird, wobbly orbit of Mercury. This table lays it all out perfectly. When you're talking about bending starlight that's just passing by the sun, both effects contribute equally. It's a 50-50 split. But for a planet that's orbiting, they have different jobs. Time curvature is what creates that basic elliptical orbit in the first place. But it's the spatial curvature, that more space, that's the subtle effect that causes the whole ellipse to wobble. You see, for most things, the effect of this more space is so tiny you'd never notice it. That's why Newton's laws work just fine for throwing a baseball. But Mercury is super close to the sun's massive gravity well, and it just keeps going around and around and around, and every single time it completes an orbit, that little bit of extra space prevents it from closing back perfectly on its starting point. It gets nudged just a tiny bit with every single pass. And when you calculate the effect of that tiny, relentless nudge over countless orbits, what do you get? You get exactly 8%. That's it. Case closed. The mystery was solved. That more space near the sun is precisely what's making Mercury's orbit precess. So this one simple, elegant idea of more space solves one of the oldest mysteries in the solar system. But it also leaves us with one heck of a question to chew on. If this is what a little bit of spatial curvature does around our sun, what in the world happens to space and time inside a black hole, where that curvature gets stretched to the absolute infinite limit?